So, hello everyone. I'm Soliman, PhD student in University at Buffalo. I work with Professor Ravi Ranade. So I'm glad to be here. This is my first in-person convention. So today I will share my research about the effect of tensile strength and ductility of UHPC on the development length of steel reinforcement. So as a lot of presenters today talked about the use of UHPC in bridges. So the most common application in the US is the use of UHPC for bridge joints to connect precast main girders. So the main girders are erected, and then the gap between the girders is filled with UHPC to provide the joint or the bonding between the two pieces. So the force is mainly transferred from the steel rebar to the surrounding UHPC by the bearing of the steel ribs or the ribs of the rebar on the concrete. And this ribs is resisted by the diagonal bearing force. The diagonal bearing force can be divided into two components, longitudinal and transverse component. The transverse component leads to an expansion on the concrete surrounding the rebar. So this leads to the formation of radial cracks. And these cracks are resisted by the hoop resistance or the hoop tension of the concrete until the cracks reach the surface of the UHPC. So in this case, you can see the cracks on the outside as longitudinal cracks, and at that time, the bond fails. And this is called a splitting crack failure. Or if you have enough resistance or enough thickness to prevent these cracks from forming or from propagating, the longitudinal component in this case will lead to a crushing of the concrete between the steel ribs. And in this case, when you pull the rebar will be pulled out of the concrete and the concrete will still intact. In this case, we have a pull-out failure. So the splitting crack failure depends on the tensile strength and fracture toughness of the material, and the confinement depending on the cover thickness and the transverse reinforcement used, and the bonded length. The pull-out resistance depends on the compressive strength of the material and the steel rebar rib dimensions and the bonded length. So from the material point of view, or using new materials such as UHPC affects these 2 points, the tensile strength and the compressive strength. So for normal concrete, we usually know that concrete is very brittle in tension. So in most of the cases, it fails in splitting failure, which is brittle failure. But for UHPC, the bridging capacity of fibers usually provide post-cracking strength. So we expect that it will provide better splitting resistance. And at the same time, it has ultra-high compressive strength, so it will also improve the pull-out resistance. So currently, there are no design standards to determine the development length of steel rebar in UHPC, but there are published recommendations by the FHWA, according to a large research program, considering a large number of parameters. So they propose recommendations with a rebar size ranging from number 4 to number 8, and they suggest using a minimum embedment length of 8D and minimum cover thickness of 3D, and minimum spacing between rebars, and a minimum compressive strength of 13.5 KSI. But these recommendations don't account for the tensile contribution of UHPC or the different fiber content or fiber type that can be used. So in these recommendations, all UHPCs are assumed to be the same. They don't account for different mixes or different behaviors. Other efforts from the literature relate the bond strength to the compressive strength of the material. But in this case, this equation is very conservative. So it's based on the lower limit of the UHPC strength. And other equations as well relate the bond strength to the fiber content and the tensile strength of the material. But this equation was based on a limited number of studies. So in general, the effect of the tensile behavior of UHPC is studied by changing the fiber content. So studying different fiber volume fractions to see their effect. So as we expect, by increasing the fiber content, the behavior or the strength of UHPC improves. So this leads to an improvement in the bond strength. So in this case, we get a linear improvement in the bond strength with respect to the fiber volume fraction from 0 to 3% for different rebar sizes. And also the bridging capacity or the bridging effect of the fibers improves. So this leads to the formation of larger number of micro cracks as opposed to macro cracks for the case of UHPC without fibers. But on the other side, the effect of other parameters like the strain capacity, for example, was not studied for UHPC, but for other fiber reinforced composites like in this study. So here the authors compared the behavior of different fiber reinforced composites, so all of them with 2% fibers. And this figure shows the uniaxial stress strain behavior in tension of different materials. So some of them had very high tensile strength and high strain capacity, like these two with the square twisted fibers and the rectangular twisted fibers. Another material with PE fibers had low tensile strength, but higher strain capacity. So by doing pull-out tests on these specimens, they found that these three materials that had the highest strain capacity showed the best bond strength. So they showed around 50% higher strength compared to the specimen with just spiral reinforcement. So here, replacing the spiral reinforcement with 2% fibers led to much higher bond strength. They also showed higher bond strength compared to slurry infiltrated fiber concrete or SIFCON with 9.7% fibers. So the main finding here is that the strain capacity of the composite itself provides much better bond strength with the steel rebar. So the objective here is to compare different tensile behaviors of UHPC. So I'm using three types of UHPC in this study. So the first one uses smooth straight steel fibers. So these are 13 millimeter by 0.2 millimeter fibers. So when doing a uniaxial tension test on this specimen, we usually get one or two main cracks, and it has a moderate tensile strength and strain softening behavior. The second mix uses the same type of fibers, but additionally, the matrix itself is reinforced by using steel wool. So the steel wool are obtained from recycling metal scrap. So they are usually much smaller size than the fibers. So the median length in this case was 1.2 millimeter. So the steel wool themselves reinforce the matrix around the fibers. So they improve the bond between the matrix and the fibers, and they lead to much higher tensile strength in this case, but the same strain softening behavior. The third mix is a strain hardening UHPC mix. So this one uses different matrix and polyethylene fibers in this case. So this mix has a slightly lower tensile strength, but much higher strain capacity. So the goal here is to compare the three different performances. One of them in blue represents the most common UHPC. The one in red represents high tensile strength UHPC, and one in black represents strain hardening UHPC. So for the rest of the presentation, for simplification, I will just refer to these three materials with the name of the fibers. So for the first one, I will refer to it as SF, the second one SFW, and the third one PE. So these are the mechanical strength of these three mixes. The compressive strength of the first two mixes was close, so slightly lower in the second mix. So 151 in the first, 136 in the second, and 119 in the third one. The most important parameter is the tensile strength and the strain capacity. So here the first mix was 7.3, 10.6, the second mix, and the third mix 6.1. The first two mixes were strain softening, so they had very low strain capacity, but the third mix showed multiple cracking and strain hardening behavior, so it reached 6.6% strain. The other studied parameters here are the cover thickness. So I used two cover thicknesses of 1.5D and 2.5D, and the embedment length. So in the first case, I used embedment length ranging from 3 to 8D, and in the second case, ranging from 2 to 6D. So when testing the bond, the most optimum test setup is to do beam setup and to have this splice region at the uniform tensile yield or tensile stress of the steel rebar until reaching the yield. But the beam tests are expensive and very time consuming, so it's not easy to do beam tests to study large number of parameters. So instead of doing beam tests, I did a modified double pull-out test. So in this setup, the steel rebar here in blue is pulled to one side, and the UHPC block is supported from the other side in tension. So the goal here is to have the rebar in tension and the surrounding UHPC in tension as well to represent the same stress or the closest stress field as the beam case. So this is a figure of the mold before casting the specimens. So I used a PVC pipe of 2-inch here to prevent any damage at the edge or prevent cone failure. And the concrete is supported from the other side with these two threaded rods. The specimens are tested in tension, so the specimens are supported at the top with these by connecting them to this steel plate, and the steel rebar is pulled downwards using this pie-shaped setup. And the slip between the steel rebar and the UHPC is measured with 2 linear potentiometers at the 2 sides of the steel rebar. So most of the specimens here failed by splitting failure. This figure shows the bond capacity of the different configurations of the 3 materials. So the figure at the top shows the bond capacity with cover thickness 1.5D, the second figure with cover 2.5D. These dotted lines represent the yield strength of the steel rebar. So our goal usually when we design or when we calculate the development length is to achieve or to reach the yield strength of the rebar. So you can see here a large number of configurations have achieved or have reached the yield strength, especially in the second case with larger cover thickness. And in all of the cases, they showed almost linear behavior with respect to the embedment length. And from the material side, the SFW material, so the material with the steel fiber and steel wool, showed the highest strength in all of the configurations. So on average, it was 15% higher than the SF mix. And the PE mix in this case was the lowest strength. So it was on average 30% lower than the SF mix. So these are the pull-out load versus slip curves. So as I mentioned, for normal concrete, we usually get brittle failure. But in this case, with UHPC, due to the fiber's contribution, none of them showed the brittle behavior. So all of them failed in a ductile behavior. It's also interesting to notice that for the 2 materials, SF and SFW, both of them show almost a linear behavior until 80 or 90% of the peak strength. And after that, the crack starts to happen and the fibers start to bridge the crack and show some hardening behavior until reaching the peak, and then the strength drops. For the case of PE material, here it shows the linear behavior until 50 or 60% of the peak strength, and then the cracks form earlier. And here the strain hardening behavior appears by forming multiple cracking and until reaching the peak, and then the strength drops. And the same behavior is observed for the case of cover 2.5D, but here more specimens have reached the yield strength. So again, by this dotted line. For the specimens that have exceeded the yield strength, they also show a hardening behavior or bilinear behavior. But this hardening is not due to cracking, it's due to the yielding of the rebar, because when the rebar yields, it deforms larger deformation, so the cross-section reduces due to the Poisson's effect. So that's why the stiffness of the bond decreases, so it shows this bilinear behavior. So to compare different materials, I compared the energy dissipated by different specimens. So to do that, first I got the normalized curve by dividing the pull-out values by the peak capacity of each specimen. So each specimen in this case goes from 0 to 1, and then the energy dissipation is calculated as the area under the curve until the load drops to 50% of the peak strength. So it was found that in the first cover thickness of 1.5D, the PE dissipates higher energy, so on average 15% compared to the other 2 mixes. And in the case of 2.5D, the other 2 mixes dissipate higher energy due to the yielding of the steel rebar, because most of them have exceeded the yield of the steel rebar. And different cracking behavior was observed in different materials. So the first 2 materials with the steel fibers usually show 1 or 2 main cracks, and then this crack localizes and starts to open. On the other side, when using the PE, UHPC, or the strain hardening material, it doesn't show just 1 crack, it shows a large number of fine cracks. And in the end, one of these cracks localize and starts to open. So the effect of material strength on the bond capacity in this case is considered. So it was found that the tensile strength is directly related to the bond capacity of the specimen. So a nearly linear relationship can be obtained here between the tensile strength of the material and the bond capacity for the 8 different configurations studied here. So the average R square value for these different curves is 0.79, which indicates good correlation. On the other side, when comparing the compressive strength of materials, which is usually used for design, with the bond strength, we don't get the same behavior, so we get worse correlation with average R square value of 0.5. So the reason for this behavior is due to the failure mode. So most of the specimens here failed by splitting failure. So the splitting failure is usually governed by the tensile strength or the tensile behavior of the material more than the compressive behavior. To compare these results of UHPC with existing design standards, so the ACI 318 uses the equation proposed by Orangum in 1977 to estimate the average bond strength, and then this equation is used to determine the development length. So I have used this equation to determine the predicted strength for different configurations, and then I compared the ratio of the real strength that I got from the test divided by this predicted strength for different embedment length for the 3 materials. So you see here, most of the points lie much higher than 1. So the average values of different materials are shown here. So the highest average one is for SFW, and the lowest one is for PE in this case. And then I did the same for the ACI 408 by using the proposed equation to determine the bond capacity. And also here, this figure shows the ratio between the real over the predicted strength for different embedment length. And these are the average values. So to conclude, so the use of UHPC provides superior mechanical properties compared to normal concrete, as we know. So these superior properties lead to much better bond strength. So the use of the current design or the current standard equations underestimates the behavior of UHPC because it usually relates the bond strength just to the compressive strength of the material. So in this study, it was found that the bond capacity is directly related to the tensile strength of the material, not to the compressive strength. And the tensile ductility had no significant effect on the bond strength, but it had a more effect on the energy dissipation or the ductility of the mix. Thank you.
Thank you, Amir.